Okay, fine. Then in today's session, we will see the topics in magnetostatics, that is Ampere's law, and the magnetic field intensity due to the different type of distributions that you have seen, the line current. And we will discuss about what is the magnetic field exists in a coaxial cable. Sorry, just a second. This is not the copy. Right. In this session, we have seen one of the Maxwell's equations, that is Ampere's law. So what is the Ampere's law says? So when you have a current carrying wire, and you know that the magnetic field will be developed around the wire. So the line integral of the magnetic field intensity in a closed loop is equivalent to the current which is enclosed. So we'll use the same Ampere's law to find out the magnetic field intensity calculations if we know the type of current distribution. So similarly, there are two steps involved in it, like what we have discussed in Gauss law. So the first step was you need to enclose the source with a closed line. The closed line means the closed line should be able to capture the total magnetic flux generated by the current carrying wire at least once. And at the same time, the line has to be symmetrical. So this is that what we have discussed in the Gauss law. And the second thing was, once you know the type of current, find out what is the total current associated with that, and then you can apply the Ampere's law. So suppose if you have any current carrying element, so that element has to be enclosed with a closed line. That is the first step. And that line has to be symmetrical. And the second thing, you can apply the Ampere's law to find out magnetic field intensity. Why? Because you can see the equation here. If you know the type of current, the current is known, you can easily define what is the magnetic field intensity. Or suppose if you want to go in a conventional method, what you have to do, you have to make use of the Biot-Savart's law. So suppose if you have a current carrying element like this, if I want to calculate the magnetic field intensity, you take a small current element here, that is a small cross-sectional length, and find out the magnetic field intensity at the observer position, and then you can integrate. So that is a conventional way of doing the magnetic field intensity calculations, but the Ampere's law has been makes the problem simpler. So like the Gauss law has been make the problem simpler, and the same thing you can do it with the Coulomb's law as well. So right now we'll see how to apply the Ampere's law. So first, in the first thing, we'll try to apply the magnetic field intensity due to an infinite line current. So you can see here, this is an infinite current element which is located along z-axis. And whenever there is a current flowing in this wire, the magnetic field is going to produce around the wire. So in the last class, I have told you what is this direction in which the flux is developed. Did you remember? In which direction the magnetic flux will be developed when the current is flowing in z direction? Good. The magnetic field is able to provide in the phi direction. So the next thing was, I have assumed a loop around this wire. Is it symmetrical or not? So this is my particular point of interest where I have to define the magnetic field intensity. So I was finding the magnetic field intensity at a radial distance of rho. First was I enclosed the source with a closed line. So this line is also symmetrical because you can see here, wherever you have considered the point, it will be equal distance from the source. You will be always at equal distance from the source. So in that way, the symmetry is ensured. And the second thing was, you can apply the straight away Ampere's law. So what is Ampere's law says? So integral h dot dl is equals to I enclose. And since you have considered only one loop here, the amount of the current considered is said to be I amperes. So you can take h as a constant, and the closed line integral along a circle is nothing but the circumference. So the circumference of the circle here, 2 pi rho. So 2 pi r is the radius. So r is the radius, I will replace with the rho. So hence the magnetic field intensity is given by I divided by 2 pi rho. So straight away the problem has been solved within 2 steps. Or else if you want to do the same thing using your Biot-Savart's law, you have to take a small elementary length here and find the differential magnetic field. Then you can integrate it. So that method also we'll try to see in the next session. So the problem is here simple when you apply the Ampere's law. And what is the direction here? So once again try to recollect what we have seen in the magnetic field intensity. The magnetic field intensity direction will be the cross product of current element into radial element. So since the current is flowing in the z direction here is nothing but rho. So when you are moving from the source, you are moving in the direction where the rho is getting changes. So that represents your radial direction. So the magnetic field will be in phi direction. So this is a formula which represents the magnetic field due to an infinite line current. So any questions you can ask at this point. The magnetic field is trying to rotate in this particular, whenever this particular point is concerned, this phi is a generalized direction, right? But at this particular point, if we consider, let us say specifically speaking, the point P has been located in the x direction, okay, on the x-axis. In that case, what will happen? The magnetic field will be straight away, you can say AZ cross AX, fine? Yes. So in that case, it will be AY direction. Yes. So depends on the particular point, that will be. So I was generalizing it here because the moment once you go in this particular loop, the magnetic field is there in the phi direction. Suppose if the observer is not located in the xy plane, okay, not on the x-axis and not on the y-axis, then which component you can say? Straight away it is phi direction, right? So whenever the observer is located in the xy plane, how will you characterize? Definitely rho, right? But whatever the radial distance, you are going to consider it as rho instead of x, right? So that is the reason why this is a generalized. So a phi can be equal to ay provided that if the observer lies in the x direction. Okay. Understood? Yes. So then we'll go ahead. So in the same, the approach remains same irrespective of whatever the type of the distribution it will be. So now I try to discuss the magnetic field intensity due to the surface current. So this is very important. You have to concentrate here more. So I have a sheet of current which is carrying a current and located in the xy plane. And the current density lies in the direction of x. That means the current is flowing in the direction of x. And if I define the surface current density as K, can you tell me what is the total current enclosed by the sheet? K into B, very good. Because the surface current is flowing in the x direction, and to find out the total current, that is the surface current density multiplied with dimension which is perpendicular to the surface current. So here B is perpendicular to the current density. So the total current enclosed by this sheet I is equal to K into B. Good. Now, the moment once the surface current is flowing in x direction, first of all, I would like to take a loop, right? The first thing was the surface current has to be enclosed with a closed line. So I have a basic question. Should I consider a loop along the x direction or should I consider a loop along the y direction? The point is that. So in which direction you have to consider the loop? In other words, if you go back to this slide, y direction somebody is telling, fine, good. So in the previous case, you can see here, this is your infinite line current, right? So I told you, right, the source should be enclosed with a closed line. So why don't you consider a loop in this following direction? So can you answer me this one? Are you able to get? So I have placed a current carrying element in the Z direction. Why don't you consider a loop along the length of the source? Why you have to consider around the source? So already one person replied per. Good, very good. Still any other answers you can give? No magnetic field there. Since it is an infinite line in Z. No, the basic thing is very simple, Pa. So you know that the magnetic field, wherever the magnetic field direction will be there, in the same direction you need to consider the loop. That is a concept. You see your Ampere's law, you can see here. Suppose if you take the magnetic field in X direction and if you consider the loop in Y direction, what will happen? Your current enclosure will be zero. So the current will be provided that the loop also has to be considered in the same direction of magnetic field. So since this is a current carrying element which produces the flux in the phi direction, you have to consider the loop also in the same direction. Right? So the point is clear. Now, in the same fashion, I have to consider loop in the y direction, something like this. So I have to consider a loop along the y direction. So I have considered a loop something like this. The reason was the magnetic field is existing in that direction only. So let me analyze why it is there. Since the circuit is flowing along the x direction, so since the surface current is located along the x direction, the magnetic field will not be lies in the x direction because the magnetic field will be always perpendicular to the current direction. So in this sheet, since the current is flowing in the x direction, there is no component of magnetic field which is in the x direction. Now, will there be any magnetic field in the z direction? So right now this is the x direction and this is the y direction. Do you have any component of magnetic field which lies in the z direction? That we'll see later. In other words, first of all, we'll see the direction. So the direction of magnetic field is basically the current into radial direction. So since the current is flowing in the x direction, that will be Ax cross. And what will be the radial direction to this sheet? So the surface charge is located in the xy plane. So what will be the radial direction for this? So you can answer in the chat box. So when you have a sheet of current located in xy plane, what will be the radial direction with respect to the sheet? So radial direction means it's a perpendicular direction. Since from the first class I was telling the same thing. So when you consider an xy plane, the perpendicular direction is nothing but z. Good. So the perpendicular direction is nothing but z. So when you have Ax cross Az, you are going to get a y component. It is positive y or negative y, it doesn't matter. So the magnetic field is going to be directed in the direction of y direction. So the magnetic field lies in the y direction. So that is the first reason why I have considered a loop along the y direction. Now, so let me start with this particular loop. So 1 prime and go back to 2, 2 to 2 prime and again come back to 1. So this is the primary loop first I was initially considering. So this is the sheet current and I have enclosed this sheet current with the following loop. So 1 prime is near to the sheet. That's what I was considering. And in the next case, I was extending the loop something like this 3 prime and 2 prime and again back to 3. So let me go case by case. So I will start with a 1 prime, 2 prime and again back to 1. So this is a loop I was considering. So what is the Ampere's law says right now? The line integral of magnetic field intensity in a closed line is equal to the current enclosed. So what it says, when you take any closed loop, the line integral of magnetic field intensity is equal to I enclosed. Now, what will happen when you split the integration? So let me do it from 1 to 1 prime. So when you are doing it from 1 to 1 prime, you are moving in the negative y direction. Correct? So let me call the magnetic field itself Hy1. So this is 1 to 1 prime. I was considering the magnetic field component as some Hy1 into the length covered will be B. And you can see here 1 prime to 2, there is no component of magnetic field which lies in the Z direction. If you see clearly, 1 prime to 2 is the direction which is perpendicular to the sheet. So when you move perpendicular to the sheet, obviously there is no component of magnetic field which you can ignore it. So I was not going to consider that. And when you are moving from 2 to 2 prime, what is going to happen? So when you are moving from to 1 prime and 2 to 2 prime, your length will be exactly opposite. You are considering the dl vector. So in 1 to 1 prime negative y and 2 to 2 prime it will be the positive y. So you are going to get a component, let me say some Hy2 is the magnetic field, and this time I will consider minus B because you are moving in the opposite direction. So up to this, any questions you have at this point?
Can you please repeat why will not consider 1 prime to 2?
Yeah, when you are moving from 1 prime to 2, actually in which direction you are moving? Are you moving perpendicular to the sheet or parallel to the sheet?
Parallel to the sheet.
Parallel.
That is, yes, sir. Explain.
Hello.
Hello. Yes, yes.
That loop is perpendicular to the sheet. This whole loop, 2 prime to 3 prime 3.
No, here when you are moving from 1 to 1 prime, you are moving parallel to the sheet in y direction. Is it clear?
Okay.
First point.
Yes.
And when you are moving from 1 prime to 2, what will happen? That is, I was representing it something like this, but actually the loop is considered going perpendicular to that and again coming back parallel. So 1 to 1 prime is lies on the top side of the sheet. Okay.
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 Y
On the
direction.
upper side of the sheet. You got the point? And 2 to 2 prime, when you are moving on the bottom side of the sheet.
Okay.
Okay.
Up to down or perpendicularly on the sheet.
Yes.
Okay.
So when you are moving on the 1 to 1 prime, you are moving in the y direction and you are lies on the top of the sheet.
Yes.
Now 1 prime to 2, I was below the sheet. So I have to move perpendicularly.
Yeah, perpendicularly.
Correct? So when you are moving perpendicularly, which direction represents perpendicular? Because the
Z.
sheet is in xy plane. So which direction will be perpendicular?
Z direction.
Now you got the point, right? So in a z direction, the magnetic field direction only will not be there, right? You already know that the magnetic field lies in y direction.
Yes, sir.
Because in the previous I have seen. So magnetic field lies in y direction and your differential length lies in z direction. So what is ay dot az?
0.
Y dot AZ.
0. Right? So that is the reason why I was not considering any, that means there is no current which is enclosed when you are moving from 1 prime to 2. And again, you can see from 2 to 2, you are moving opposite direction of 1 to 1 prime. So when you are moving from 1 to 1 prime, you have considered something as a B. So when you are going from 2 to 2 prime, it should be minus B. Correct? Understood? All
Yes.
of you? Right. So and again from 2 prime to 1 you can neglect because this is the Z direction. Nothing will be there. So what is the final magnetic field you are going to get now? Hy1 into B minus Hy2 into B is equal to, and the total current enclosed is nothing but, let me call it as I simply. And so what will happen? Hy1 minus Hy2 is equal to I by B. So current divided by B is nothing but your surface current density. So take it as equation 1. Now I will write the same thing by creating the loop something like what 3 prime 2 2 and again to 3. So this time I was considering from here I was going down and coming here and again here and here. So this is the loop I was considering. So in the same fashion, what will happen when you are moving from 3 to 3 prime? So I was assuming whatever the magnetic field from 1 to 1 prime will be different when you are moving from 3 to 3 prime. I was assuming that. Okay. So let me define that magnetic field component as H by 3 into you have covered a length of B. Same as that. And again, what will happen when you are moving from 3 prime to 2, you are moving perpendicular to the sheet. So your H dot dl becomes 0. So again, what will happen 2 to 2 prime? So 2 to 2 prime is same as H by 2 into B. So here also when you consider in this particular loop, your Ampere's law has to be satisfied. So integral H dot dl has to be I. So what will be the total magnetic field intensity here right now? So H by 3 into B minus H by 2 into B is equal to I. So you can say H by 3 minus H by 2 is equal to I by B. So which is also said to be K. It as equation 1. So when you compare both equation 1 and equation 2, what actually represents? So see the equation 1 and equation 2. You are going to get one conclusion. So Hy1 minus Hy2 is equal to K. And here Hy3 minus Hy2 is equal to K. So when you compare both 1 and 2, you can say that Hy1 is same as Hy3. That means that whatever the magnetic field when you are moving from 1 to 1 prime is the same magnetic field when you are moving from 3 prime. So can you comment what is the meaning of that? 1 to 1 prime means when you are moving from 1 to 1 prime, are you near to the source or far away from the source? So when you are moving from 1 to 1 prime, are you moving near to the source or far away from the source? You can answer. Am I audible for everyone? Near to the source. Correct. So Hy1 is the magnetic field when you are moving near to the sheet, and Hy3 is the magnetic field when you are moving very far away from the source. So what it says here, this conclusion says, irrespective of the position, so if this is the sheet of current and whether you are near to the source or far away from the source, the magnetic field intensity magnitude remains same. That's what we have seen here. So which I can say that the magnetic field is independent of the distance.
Sir?
Correct? Yeah, yes.
But this 3 dash and 2 dash are actually the plates which are parallel to that current, right?
No, it's perpendicular to the current
Top
only
and
because parallel to the sheet.
yes, sir. It is on the top sheet and the bottom sheet, right, sir?
Yes, 3 to 3 prime when you are moving on the top side of the surface, but it's this time it's quite far. Okay.
Quite far in the sense far from the sheet or like.
Far from the sheet. So
Okay,
sheet
sir.
is located in the horizontal plane, right? So this time you are increasing the distance. Instead of taking the loop closer to the sheet, you have extended the loop. That means far from the sheet.
Okay, sir.
Yeah. And again, I was remaining 2 to 2 prime as same as that. So by comparing equation 1 and 2, what I was getting the conclusion. So even when you consider a loop in the y direction, one time near, and you are considering the same loop parallel to the y-axis, but slightly you are moving very far away from the source. So whether you move away from the source or near to the source, as long as you are moving parallel to y-axis, the magnetic field intensity remains same. And at the same time, I can say that one more conclusion I can say here. whatever the magnetic field on the back side of the sheet, HY2 is the magnetic field on the bottom side, is equal to the magnetic field on the front side with a new sign. Is my statement correct? Can anyone justify this? So the magnetic field exists on the bottom side is exactly same as the magnetic field on the top side, because right now we have seen it is independent of the distance. But when you consider a magnetic field at the bottom of the sheet, it is, I have considered minus HY1. Can anybody justify this reason? What will be the reason for this?
So they form closed loops. That's why.
Closed loop. Closed loop means that is fine. Yeah.
Yeah, the magnetic fields like they are always closed loops. Means the amount of flux entering will be always the amount of flux leaving.
Fine. Instead of that, I can let me define it in a different way. You know that the direction of magnetic field is equal to current into radial direction, right?
Yes, sir.
So this is your XY plane. You can see here, this is your XY plane. So what is the radial direction here? This will be positive Z, right?
Yes.
This will be positive Z and this will be negative Z. So suppose, so this is the loop you have considered. When you are on the top side, what will be the magnetic field direction you can say? Current direction is same. So let me define the surface current is in the X direction. When you are on the top of the surface, when you are on this particular point, so this is your sheet and you are on the top of the surface, what will be the radial direction here? Is it positive Z or negative Z? Good, it's a positive Z. What will happen when you are below the sheet?
Negative.
Negative Z, right? Because radial direction means source to observer. Suppose if the observer is on the top side of the sheet, your radial direction will be on the positive Z axis. Similarly, if the observer is at the bottom of the sheet, it will be negative Z. So what happened here? Your radial direction got changed. So when you are moving on the top side, your radial direction is, let me say, plus AY. And when you are moving on the bottom side, your radial direction is minus AY. So because of this change in the radial direction, the magnetic field intensity also gets minus, negative sign. But what will happen? Suppose if you consider 2 points on the top side, whatever the magnetic field intensity here and here, both remain same, even in magnitude as well as the polarity. Suppose if you consider 1 point on the top side and 1 point on the bottom side, the magnetic field intensity magnitude is same, but the direction is different. You got the point, everyone?
Yes.
Right. Substitute H2 is equal to minus HY1 in the equation 1. So when you substitute equation 4 in equation 1, what you are going to get? So I can say HY1, and instead of minus HY2, minus HY2 is minus of HY1 is equal to K. So what will happen? 2 times the magnetic field intensity on HY1 is equal to K. So what is the value of HY here? Y1 is equal to K by 2. So the magnitude of the magnetic field intensity will be half of the surface current. And suppose this is when you are moving on the 1 to 1 prime, right? Even 3 to 3 prime also magnitude will be K by 2. But when you are moving from 2 to 2 prime, it will be minus K by 2. Okay, someone is asking me to repeat. Which point you want me to repeat? Yes,
So,
yes.
sir,
Which?
that second slide, the later slide, you showed that one sheet is there, perpendicular direction, up
Correct.
and down side.
Yeah.
So there, can you explain that how that magnetic field direction is
Opposite.
which side?
Direction will be opposite, right? That is a point, right? So see here, this is your XY plane. And see, this is the X direction and this is your Y direction. And perpendicular to the sheet, you have the Z direction. So
Okay.
this will be positive Z and this will be negative Z. Now what will happen when you take an observer point which is above the sheet. What will be the direction? Let me say this is point A, and one point I have considered below the sheet, right? So when you are finding the direction of magnetic field at point A, what will happen? Current remains same. Current lies in x direction.
Yes.
And what will be the radial direction? So since the
Oh,
point is on
yes.
the top side, the radial direction will be from source to observer.
Okay.
So you are going to move it in the positive z. Is it clear?
Yes.
Now similarly, when you are on the bottom side, current remains same. And what about the radial direction here?
Negative Z.
Yeah. Now you got the point. So this you are going to get minus ay, and this you are going to get plus ay. You got the point right now?
Okay. And that intensity will be same.
The intensity will be same.
Direction.
Just with the help of mathematics, I shown you, right? Because when you
Hmm.
compare the two equations, you are going to get the intensity remains same.
Okay.
So if we compare the equation 1 and equation 2, what you are going to get based on these two, Hy1 remains same as Hy3. So intensity is same. So when you are putting it finally, you are going to get the magnitude as half surface current. So in when you summarize it, so I can say that the magnetic field due to a surface current due to a surface current will be given by the magnitude is k by 2, and including the direction, if the direction will be element direction with the radial direction. So this is the generalized equation you can use when you go to any problems. If you see here the magnitude is k by 2. But if you want to speak in terms of direction also, the direction, yeah.
Hello.
Yeah, yes.
Yeah. So that the last point you told that H1 and Hy1 Hy1 and Hy3, these two are sorry, Hy3 and Hy1, these two that direction same and magnitude also is same, right?
See, first, what is the first equation you had? You got Hy1 minus Hy2 is equal to k. This is your first equation, right?
Yes.
And what is the conclusion you got right now? I told you, because Hy2 is when you are moving on the bottom of the sheet.
Yes.
And H when you are moving on the top side. Correct?
Yes. Yes.
So what is the conclusion I given? Hy2 is equal to minus of Hy1. Just now we explained.
Okay.
So whatever the magnetic field on the front side, it will be same on the back side also with negative sign. That is what I have written here. Agree?
Yes. Yes.
So now if we substitute the same thing, this equation in this particular equation, what we will get? Hy1 minus Hy2 is minus of Hy1.
Yes.
Agree? So what
Yes.
you are going to get? 2Hy1 is equal to k. So your Hy1 remains k by 2. Agree?
Yes. Yes.
So Hy1 is k by 2 means your Hy3 is also k by 2. Agree with my point?
Yes. Yes.
So that's what. So instead, what you are getting, irrespective of the point, you are going to get the magnitude as k by 2. Now I was generalizing it in this vector form. So if you look at this one, the magnitude will be k by 2. This remains same. And including the direction, if you want to write, the direction of magnetic field will be cross product of current into radial direction. So in the same example, suppose you consider the observer lies on the top side of the sheet. So whatever the surface current is there, the observer is located on the top side. In that case, what will happen? So k by 2, when it is on the top side, the perpendicular direction will be az. That's it. So you know that k by 2 is the magnitude and the surface current is lies in x direction and the radial direction is z. So when you are on the bottom side, what will happen? The magnitude k by 2 remains same and the surface current also in x direction and the radial direction will be minus az. So I was giving a generalized equation. So where you can apply this formula, whether it is on the top, on the above the sheet or below the sheet, you can generalize the formula like this. So I hope this is clear for you, everyone, right? Shall I go ahead? Shall I continue? Yeah. So let us try to find out the magnetic field due to a finite line of current. So instead of having an infinite line current till now what we have discussed, so this time we will try to see the magnetic field intensity due to a finite line current. So the first thing was here you cannot apply the Ampere's law. The reason was the Ampere's law is applicable for all symmetrical surfaces and there should not be any discontinuity in the current. So when you take an infinite line, you can assume that the current is infinitely flowing from one end to the other end. So there is no discontinuity at any point. So in those cases only the Ampere's law will be applicable. Suppose what will happen when you take a finite line current? So the current is flowing over a particular length only. So it's not infinitely extending. So when you are seeing at the edges, there is a discontinuity in the current that will exist. So especially when you are taking a finite line current, the current distribution is non-uniform at the edges, whether it is the lowest edge or the upper edge. So what happened? Just below this edge, there is no current. Similarly, above this edge, there is no current. So the Ampere's law cannot be applicable. But of course, you can make an approximation. So whatever you are going to get with the Ampere's law is approximated even in this case also. But I have considered this topic just to explain how you can find out the magnetic field using the conventional technique of Biot-Savart's law. So that is the main intention. So when you consider this finite line current, you can see here, and this is located along Z direction. And this is my point of interest where I have to define the magnetic field intensity. So this is my current carrying element and this is my position of the observer. So for that what I have taken a small current element here. So first I will try to find out what is the magnetic field intensity due to this current element. Then I will integrate from this edge to this particular edge. Okay, so what is the Biot-Savart's law says right now? The differential magnetic field due to a small current element is given as, so right now you can see here I into dl is nothing but dz prime. So this differential length I have considered here as dz prime cross product with the radial direction, that is nothing but ar cap divided by 4 pi r square. So this is the same expression using the Biot-Savart's law. The same thing I have been written. So what will be the unit vector along r direction here right now? Next thing. So ar cap is the unit vector along this particular radial direction. So you can see here from here to here and from here to here again you come back here and again here to here. So when you are moving from O to P, you are moving in which direction? Can you tell me? When I was moving in this particular direction, what will be the change that will happen? In which direction there is a change happen? Rho, correct. So you can see here this particular distance is rho. So I can call this vector as rho into aero cap. Similarly, when I was moving from here to here, so the current element is located at 0, 0, z prime. So this vector I can call it as z prime into az cap. And from here to here, that means source to observer, this one I have called it as r bar. So using the triangular vector law of addition, what will happen? So when you are starting from here, so z prime into az cap plus the vector r bar is equal to rho into aero cap. So using the triangular law of addition, what will happen? This vector plus this vector should be the resultant equal to rho aero cap. So what you are going to get? Z prime into az cap plus r bar is equal to rho into aero cap. So in other words, what I can say, r bar is equal to rho aero cap minus z prime az cap. And what will be the modulus of r bar right now? So that will be root over rho square plus z prime whole square. So what you are going to get right now, the unit vector along r bar equal to rho aero cap as z prime az cap divided by rho square z whole square whole power 1 by 2. So I am going to get unit vector, and at the same time you dz prime, if you want to write the particular vector, so that current element is located in the z direction. So what will happen to the differential magnetic? So I into dz prime, and this is located in which direction? dz direction. Cross product with, so ar cap, I can directly substitute this value. So what you are going to get, rho aero cap minus z prime az cap divided by 4 pi. So in the ar cap also, in the denominator 1 r is there, and this r square is there. Total r cube we will have. So we will get r cube will be rho square plus z prime whole square whole power 3 by 2. So any questions you have, you can ask me now. Up to this one. Are you able to follow what I am saying? You can reply. If you have any doubts, I will once again explain, because this method you need to understand. That is my intention. Yes.
So direction of DH will be AZ cross arrow. That will be the direction.
Which direction? Which direction?
This DH direction.
Yeah. See, if you see the current element is located in the direction. You see here, the current element is located in the direction. And the direction of magnetic will be current direction cross product with radial direction. So what is the radial direction here? Radial direction means r bar. So that's what I was substituting here. So this is your bias. So first of all, I am writing a unit vector along the radial direction. So how to write a unit vector along radial direction? The original vector divided by the modulus. Right? Now how to write the original vector? So simple reason. So this is your vector a bar, okay? And this is your vector b bar. And this is your vector c bar. So when you start from here, so a bar plus b bar is equal to c bar. Will you agree with me?
Yes.
So what is a bar here? A bar is equivalent to prime into az cap. And b bar is but your resultant vector, r bar, is equal to c bar. C bar is nothing but rho into aero cap. You got the point?
Yes.
Yeah. So the same thing I was directly substituting. Nothing else is there. So now, when you see the magnitude part, what you will get? When you take the cross product, what will here? Az cross aero will be. Agree? And the other component will z cross az. That is straight away 0. So because of this one, you are going to get the magnitude. So I was straight away multiply component. You multiply the component with az and by component with az. So when you are multiplying row component within direction phi, that is good. And whereas when you take az cross product with az, the cross product of two similar vector is 0. So the resultant direction will be lies in phi direction only. And what will happen to the magnitude part? I into rho into dz prime divided by 4 pi rho square plus z whole square whole power 3 by 2. Could you just repeat? I got disconnected in the middle. Are you getting? Prudvi. So you got the point, or from which point I need to start here to explain?
Sir, from I guess last but second point, sir.
Okay, this particular point, this one?
Yes, sir.
Yeah. So first of all, this point is clear for you, the differential magnetic field. This is the same expression of Biot-Savart's law, right?
Yes, sir.
The current element cross product with radial direction divided by 4 pi r square. So did you get how I am writing the vector r bar? This point is
Yes,
clear right
sir.
now,
Yes, sir.
right? So the magnitude of r bar will be straight away root over rho square plus z prime whole square. Now, what I was doing here, AR is replaced with r bar modulus of r bar. Okay, when you see this equation, how this equation is going to become? So I into dz prime divided by AR cap, I can write it as r bar by modulus of r bar. So in the denominator already r is there. So denominator becomes r cube. You got my point. Now after
Yes,
that,
sir.
what I have done, r bar is replaced with this vector. So r bar I have replaced with this particular vector. And modulus of r I was with this one. So the same thing. Is it clear right now?
Yes, sir.
Yeah. So finally, this is your magnetic field intensity due to a small current element. Correct. So once again, I will clear the slide and I will write. So what is the value you are going to get right now? I rho dz prime divided by 4 pi into rho square plus z dash square whole power 3 by 2. So this is a magnetic field intensity due to this small current element. Now I want to find out the total magnetic field, right? So if you want to get the total magnetic field, you need to integrate. So you need to integrate this something like I rho dz prime divided by 4 pi rho square plus z prime whole square whole power 3 by 2. So to make the integration convergent, I will convert all this length in terms of angle so that it is easy for me to do. Now, all of you can see this triangular. You can see this particular triangle. So whatever I was writing, you can see this particular triangle. So in this particular triangle, there is a 90 degrees angle here. And you know that this length will be z prime and this length will be rho. So what is the value of tan alpha here? Tan alpha is nothing but the opposite side z prime divided by the adjacent side. That will be is equal to rho. So this is your tan alpha, right? This is your alpha. So when you are applying tan alpha, that will be z prime divided by rho. So what you can do the conversion using this variable, z prime is equal to rho tan alpha. So this is your equation 1. So in that case, what will happen? Dz prime becomes, you can differentiate that. So rho into secant square alpha into d alpha. So I was converting the variable z in terms of angle. So since it is very easy for me, because the moment once you convert z into angle, so when you are integrating it, you can integrate from the lower angle to the upper angle. Lower angle is nothing but alpha 1 and upper angle is to alpha 2. So I was doing the transformation of the variable by using this trigonometric. So now you can substitute the same thing, what you are going to get. So h is equal to I rho. So dz prime will be rho secant square alpha d alpha by 4 pi plus rho square plus z prime whole square is nothing but rho square tan square alpha whole power 3 by 2. So what you are going to get right now? So I divided by 4 pi rho secant square alpha d alpha divided by, so rho square you can take it common, so it will finally become rho cube, and 1 plus tan square alpha is secant square alpha power 3 by 2. You are going to get secant cube alpha. So finally, what is the thing you are going to get? H is equal to I divided by 4 pi, sorry, this is rho square here. So rho square, one rho will be kept common here. So I by 4 pi rho into integration of 1 by secant alpha, that is nothing but cos alpha, d alpha. So when you want to find the magnetic field intensity right now, you can integrate from the lower edge up to the upper edge. So the lower edge is making an angle of alpha 1 and the upper edge is making an angle of alpha 2. So I was integrating from alpha 1 to alpha 2. So finally what you are going to get? So integration of cos alpha will be sin alpha. So finally you are going to get the magnetic field intensity is equal to I by 4 pi rho into sin alpha 2 minus sin alpha 1. So this is your magnetic field intensity. So once again, if anybody is not getting the derivation part, after that also you can look into that, because just my intention is at least some people can understand the way how you can find the magnetic field intensity using the Biot-Savart's law. So that is the main intention. So ultimately this formula is very important for you to solve the problem. So if anybody not got this derivation part, once again you go through the video. So try to do step by step. You will automatically get this answer. You need not to worry about that. So any questions now? Yeah. Now let me try to apply the same logic when you are going to the infinite line. So in an infinite line, what is the formula we got? In Tesla, if you remember, the magnetic field intensity due to an infinite current element, we got the relation something like this, I by 2 pi rho. We'll try to verify that using the same formula. So you can see here, this is your radial line. So this is your current carrying element. So this is your radial line. So same thing I was drawing, this is your radial line. When the line is infinitely extending, what will happen here? So when this point is trying to infinitely extending, if it is going on the positive z axis infinitely, what will happen? This line is looking to be vertical. So as this point is approaching it to plus infinity, how this line segment is going to look like? Something like this. So in that case, this is nothing but your alpha 2. Agree? And what will happen when you are pulling this side? So when you are similarly, if this line is going below, that means infinitely extending to negative z axis. So this line segment you are trying to pull, so this is going to become vertical, something like this. So your alpha 1 becomes this one. So what will happen right now? This is your radial line, and the upper is going to make an angle alpha 2, and the bottom edge is going to make an angle of alpha 1. So you can see here, alpha 2 you are measuring in anti-clockwise, so that is going to be positive. It is exactly 90 degrees. And alpha measuring in a clockwise. So whenever you are measuring in a clockwise, you should consider it as a negative. So when you measure the angle in an anti-clockwise manner, that is positive, and when you measure the angle clockwise, that is negative. So alpha 1 is clockwise, so it is negative, and it is also 90 degrees. So now you can substitute alpha 2 is plus 90 and alpha 1 is minus 90. So you are going to get the same equation, I by 2 pi rho. So that's how we can verify the Biot-Savart's law and the Amperes law. So any questions here? And one more thing I would like to clarify, this alpha 1 and alpha 2, you have to be more clear. So what do you mean by alpha 1 and alpha 2? I will explain here. So if this is the radial line, so first of all, alpha 1 and alpha 2, how you have to measure was, so suppose this is your current carrying element. Alpha 1 is the angle made by the lowest edge with respect to the radial line. So first draw a line from the lowest edge and measure the angle with respect to the radial line. So this is your alpha 1. So alpha 1 is the angle made by the lowest edge with respect to radial line. and alpha 2 is the angle made by the upper edge with respect to the radial line. And always the arrow should be pointing the radial line. So the arrow should be pointing towards the radial line. So when it is an infinite line, what will happen? This is your radial line and the upper edge becomes perpendicular like this. So this is your become alpha 2 and the bottom edge is also perpendicular. So you have to measure alpha 1. Here also you can see the arrow is always pointing to radial line. So for an infinite wire, alpha 2 will be plus 90 and alpha 1 will be minus 90. So any doubts you have in defining alpha 1 and alpha 2? So you can clarify your doubts right now, because once we go to the problem, it looks to be confusing. So that's why I was making a clear statement here. Alpha 1 is the angle made by the initial point with respect to the radial line. And alpha 2 is the angle made by the final point with respect to radial line. So radial line means, once again I will telling you, from the source to observer, that distance represents the radial line. So every concept clear? Yes?
So suppose that line is semi-infinite, then one of the angle we don't have to consider, or both angles.
No, if it is semi-infinite, one angle will be either plus 90 or minus 90. Correct?
Hello?
Correct? Isn't it? See,
I missed.
semi-infinite means it is extending from infinity to 0 only. Okay. And my object is 0. So what will happen? One angle is going to become something like this. So this is my alpha 1. Alpha 1 will be 0. And what will happen alpha 2? Since this is extending infinitely, this line becomes like this. Alpha 2 is going to become plus. Or suppose what will have? You may have a semi-infinite line from minus infinity to 0. And the observer. So that time what will happen?
Alpha 1 become minus 90 and
Very good. Alpha 1 becomes minus 90 and your alpha 2 becomes 0. Right? Semi-infinite, only one of the angle will become plus 90 or minus 90. Agree?
Yeah.
We'll see the problems also. You need not to worry. Then you will get an idea. Okay, we'll go ahead. So this word already I have discussed this concept. So I am going to skip that. So when it is an infinite element, your alpha 2 is plus 90 and 1 is minus 90. So you are going to get the magnetic field is same as that, I by 2 pi. Now, the same kind of Ampere again will come back to the Ampere's law and we'll try to the Ampere's law in a coaxial cable. So in electrostatic spot also we have seen what is the electric field intensity in a coaxial cable. That means between the conductors or inside the inner conductor or completely outside the coaxial cable. Once again, I need not explain here. If you see the coaxial cable, there is a conductor and there is an outer conductor. So when you apply any voltage to the inner conductor, the current is flowing through the inner conductor and the conductor. So the current is flowing and the outer conductor. Now, what you can say in this case right now, in other words, the inner conductor is carrying a current I in a loop area of what will be the cross-sectional area of this inner conductor. So if you see the inner conductor is having a radius of A. So the cross-sectional area of the inner conductor will be pi r square. So R is nothing but A here. So this is the current carried by the inner conductor. So I is the current enclosed in a loop area of pi A square. Similarly, the outer conductor is carrying a return current of I. So when you say that return current is nothing but minus I. So since you can see the inner conductor and outer conductor carrying the current in opposite direction. So I can say the return current of I, or you can say the minus I, is used in a loop area of how much here? This is the loop area of the conductor. pi into b square. Is it clear? The first thing. So this is the same kind of analysis we have done in the electrostatics. If we have a non-metallic solid sphere, if you consider a Gaussian surface inside, there you have seen the ratio of the volumes. So similarly, when you are talking about the current, you have to consider the cross-sectional area. So finally, the current carried by the inner conductor is I in a loop area of pi a square, and the outer conductor carries a current of minus I in a loop area of pi b square. Now we'll take case one by one case. So in the first case, let us consider a point which is less than a, which means rho less than a means you are inside the inner conductor. So let me explain in this slide, so it is better. So when you consider inside the inner conductor, what will happen? So this is your inner conductor boundary and this is your outer conductor boundary. So since enclosed in terms of area, so I was representing this diagram only the cross-sectional area of the coaxial cable. So that means when you look at the coaxial cable from the front side, you are going to look at two circles. One is your conductor and this is your outer conductor. So when you take a point somewhere here within the inner conductor, first thing what you need to do, wherever you are finding the magnetic field intensity, you assume a loop. You need to assume a small imaginary loop. So that's what I have done using the Amperes law. So that loop is to have a radius of rho. So I was calculating the magnetic field intensity, the distance of rho within an inner conductor. So the first point is when rho less than a, you are inside the inner conductor. Can you tell me what is the current enclosed? Can anybody tell me what is the current enclosed in that loop? So this is my loop I have considered. How much current is enclosed? I. No? Still, you can give another try. So first of all, when you are considering in this particular loop, what is the loop area you are covering? You can speak out, no problem. You can directly speak in mic so that we don't waste time here. So what will be the loop area when you consider a point which is less than a?
It's pi rho square.
Pi rho square, correct. So when you see the inner conductor, I told you already, the inner conductor I is enclosed in a loop area of pi a square. And whatever the loop you have considered, you are going to enclose the area of pi rho square, which is small. So how much is the total current enclosed in that case is nothing but I into pi rho square divided by pi a square. Correct?
Yes.
Understood, everyone? So since I have covering a small loop area, the amount of the current is also proportional to the area. So whatever is the original current carried by the inner conductor into the area of this loop divided by the area of the inner conductor. Now we can apply the Amperes law. So what is Amperes law says? Integral H dot dl is equal to I enclosed So you can see here H into what is the closed line integral again? Whatever the loop you have considered, the closed line integral is nothing but 2 pi is equal to I into rho square by a square. You can see here pi gets cancelled. And rho one time gets cancelled here. So the magnetic field intensity will be given by I into rho divided by 2 pi a square. So this is a magnetic field intensity when you are inside the inner conductor. So now I was giving an exercise. What will happen when you consider a loop completely out coaxial cable. That means when rho greater than B. So when rho greater than B, you do the same method and tell me what will be the magnetic field intensity. So you can take time and you can tell me, not a problem. So first of all, what is the total enclosed current when you take a loop out? So when you take a loop outside, how many number of currents you are going to enclose? So this is my rho is the radius of the imaginary loop. So what is the total enclosed current? You can reply.
So will it become zero, like I and minus I will be there?
Exactly, that is the same thing, right? Because when you take a loop outside, you are going to completely enclose the inner conductor plus outer conductor. So the inner conductor carrying a current of I and the outer conductor carries a return current. So happen finally the total current will be zero. So whenever there is no current, there won't be any magnetic field. So what will happen? Integral H dot dl is equal to enclosed. So since there is no current, there is no magnetic field. So this is the same logic I have explained even in the electrostatics also. If you have any coaxial cable, when you take a point outside the coaxial cable, even there also you can compare your electric field intensity 0. And similarly, right now we also got the magnetic field intensity also 0. So that is the reason why the coaxial cables will not cause any electromagnetic radiation. So which will not cause any interference. So that is the reason why it is mostly used in the communications. So when you consider any coaxial cable, outside the coaxial cable, there will not be any electric field and there will not be any magnetic field. Okay. So let us do the same case by considering a point between the conductors, between inner conductor and outer conductor. You can repeat the same thing and tell me the answer. Now the case 3 will be when the value of rho lies between A and B. So that is between the conductors. So I have already covered here. So this is my radius of the loop I have considered. So let me say this is the radius of the imaginary loop. So within this loop, what is the total enclosed current? So in this imaginary loop, what is the total current enclosed? Good, it is I. So because whatever the current you are enclosing in that loop is only the current carried by the inner conductor. So that is nothing but I. So then you can straight away apply the Amperes law. So integral H dot dl is equal to I. So H into 2 pi rho is equal to I. So what you are going to get, the magnetic intensity is same as I by 2 pi rho. So this is a magnetic field intensity between the conductors, between inner conductor and outer conductor. So any questions you have? So I will summarize here whatever you have discussed in the coaxial cable. I will summarize it here. So the first thing, when you consider a point within the inner conductor, you are getting the magnetic field intensity equation like this: pi into rho by 2 pi a square. So your magnetic field intensity will increase with the increase in rho. So it is directly proportional. Can you tell me the reason why? So when you are within the inner conductor, as the value of rho increases, the magnetic field intensity is going to increase. What will be the reason? This is a mathematical equation, but can you justify how it is? In other words, close to surface. So that's it. As the value of rho is trying to be bigger, you are going to have a more loop area. The moment when you have a more loop area, the current also enclosed will be more. Correct? The moment the area is going to be increases, you are going to capture the more current. Similarly, in the electrostatics also, if the volume of the Gaussian surface increases, you are going to increase the more charge. As the loop area gets larger, you are trying to capture the more current. Once the current is getting high, your magnetic field intensity also going to be high. And what will happen when it is rho lies between 0 and B? The magnetic field intensity is indirectly proportional. So I by 2 pi rho. And what will happen when it is rho greater than B? Your magnetic field intensity will be 0. So what will happen when I draw the profile here? This is my radial direction and this is my magnitude. So let me say this is on the rho axis, this is on the z axis. Consider that. And this is my inner conductor boundary and this is my outer conductor boundary. Sorry, this is rho axis. Now, when you are moving from 0 to A, that means when your rho is lesser than A, you can see here the magnetic field linearly increases. So you are going to get a linearly increasing function till up to A. And what will happen when rho lies between A to B? Sorry, this is A to B. Your magnetic field is inversely proportional to rho. So you are going to get decrease. And when rho greater than B, it is close to 0. So at what point the magnetic field intensity is maximum? You can see here the magnetic field intensity is maximum when rho is equal to A. That means when you are on the surface of the inner conductor, the magnetic field intensity is very maximum. So you can find out that value also. So what is the value of that? So if you replace rho with A here, so the maximum magnetic field occurs on the surface of the inner conductor. So when rho is equal to A, so that is equal to I by 2 pi A. This lies on the surface of the inner conductor. Clear for everyone? Any questions you can discuss before going to problems? So first of all, how is the subject flow actually? Is it difficult or is it easy? How you felt the subject till now when you compare with the other subjects?
So many formulas.
So many formulas. Then formulas is one thing actually. If you take any subject, it is quite better when you compare with EDC, right? Am I correct or not? When you come across EDC, there are so many formulas will be there, which you can't memorize also. At least in this electromagnetic theory, I was able to explain you the background of it.
Yes, sir.
So even though there are so many formulas are there, I was trying to explain it, right? So you will become to know. So whereas if you go to EDC part, when you say the width of depletion region, if you look at the derivation part, it will be mind blowing. So you have to remember the formulas without knowing the concept there. That's how it goes. But I felt it is interesting in other way. So you can see here you are going to understand the concepts basically.
Yeah, we can derive it also. Means like
Yeah, you can derive it, but the thing is one time if you derive it, you can try to memorize it. That's what you should do in all other cases also. And these things, whatever I was saying in this right now, suppose if you consider the same presentation, what I was teaching now, you need not to remember all these equations. The moment once I went to solving the problems, the only thing what you require is nothing but how to apply the Ampere's law. If you are thoroughly understand how to apply the Ampere's law, there is no need to remember any formulas. Because whatever the formulas I am going to give you, it's whatever the problems I am going to discuss, it's not memory based questions. It's all about the concept. The gate also same thing. Gate is always testing about your aptitude skills. What is the basic fundamentals you have, whether you are strong in that or not. Of course, there are some cases where actions will be there. You need to memorize the formulas. But as per today's presentation is concerned, it's all about how you are applying your concept. So the full presentation, what I have seen is nothing but how to apply the Ampere's law. So when any magnetic field intensity problem is given, first thing what you need to do was, so wherever you need to find the magnetic field intensity, you enclose the source with a closed line. And then find out what is the how many number of currents are getting enclosed in that. So find out the total enclosed current. Then you can apply the Ampere's law. That's it. So that is a method finally you need to understand. So is it clear? Any question you have?
Sir, EDC and EMT are related. Means like any concepts or like EDC is complete.
Not actually. I feel it's both are quite independent, quite different, completely different.
Okay.
Only the thing is whatever, like some of the topics where I told you right in the concept of Poisson's equation.
Okay.
So it will be applied in your PN junction diode in EDC. Of course, your professor will not be able to explain how the width of the depletion region. He will trying to give one expression something like this, right? I think you might have been come across this or not. This is the width of the depletion region in case of PN junction diode, right? So he is directly going to tell you the formulas. But this concept in the question I already told you how to derive that. That is d by dx square is equal to minus rho v by epsilon. And when you are on the p side, your rho v will be equal to Na into q. And when you are on the n side, it will be donor atoms into q. So that concept will be written in EDC, but not much. Okay. So any questions you have? Or shall we start the problem? You want break? So do you want break for 5 minutes? Okay, you take 5 minutes break, and this is 6:54 right now. We'll come back again at 7 o'clock, right? After that, we'll start the problems and we'll conclude.